Hi, in this video we're going to be talking about directional derivatives. So we just learned about our partial derivatives. And so when given a function of two variables, we find the partial with respect to x, what we're really finding is the rate of change in the x direction. Or if we're talking about our standard basis, the partial with respect to x is actually going to be the rate of change in the direction of our I hat vector. And then our partial with respect to y is going to be our rate of change in the y direction, or in the direction of our j hat vector. But we don't necessarily have to restrict ourselves to just in the x direction or with the y direction. Directional derivatives allow us to find the rate of change in, well, any direction, as long as we can define that direction in terms of a unit vector, again, typically given by u. And if we have the unit vector u, which is given with an x-coordinate of a and a y-coordinate of b in my xy plane, I can do a little bit of right triangle trig and clearly see that, well, if it has a magnitude of 1, that's really my radius, I suppose, of the hypotenuse. And simple SOHCAHTOA, obviously the x-coordinate would be cosine theta and the y-coordinate would be sine theta. And so when we define our directional derivatives, we sometimes use either one. But the main idea here is that I can now find my directional derivative in that direction of u. So just like when we did our partial derivatives, where we have our surface in 3 space and we're slicing our surface either along the x or slicing my surface along the y to find that trace, directional derivatives allow us to slice our surface, well, really in any direction we want. And we can take our unit vector u in the xy plane down here, and we're going to be able to define a plane that is parallel to u that's going to extend, well, infinitely, and will then obviously intersect my surface. Any plane that intersects my surface is going to give us a trace, or an intersection is going to be a curve, right? And then all I'm doing is trying to find what's the rate of change at a specific point on that curve. So the way our formula works for finding the directional derivative is we take our function, we find the partial derivative with respect to x, and then we multiply it by, well, the x-coordinate of our unit vector. Then we take the partial derivative with respect to y and multiply times the y-coordinate of our unit vector. And then, like I said, if we have it in terms of an angle that my unit vector makes with the x-axis, we can substitute for cosine and sine using right triangle trig. Now, if I want to find my directional derivative, and let's say I pick my unit vector as being the I hat vector, well, what's going to happen? Well, if I plug it in, again, my x-coordinate is 1. So my x-coordinate is 1, my y-coordinate is 0, my y-coordinate is 0. But what's 0 times anything? Well, it goes away. And so the only thing left is going to be the partial with respect to x times 1, but anything times 1 is, well, just itself. So yeah, obviously in the I hat direction, my directional derivative is just the partial with respect to x. It's still the exact same definition that we used before. So let's take a look at one example here. Let's say I have my surface defined as x cosine y, and I want to find the slope at the point 1, 0 as we move twice as much in the y direction than the x. All right, so I have my point, so I want to find the rate of change at that point, but as I move twice as much in the y direction than the x. And so the first step is going to be to define our direction. So I need a vector that actually describes this, well, direction that we're given in the problem. And so twice as much in the y than in the x. And the easiest way is to come up with a vector that's 1 in the x-coordinate and then twice as much, or 2 in the y, except we have an issue. We need to be really, really careful because that's not a unit vector. The magnitude of that vector is, well, square root 5. Then obviously when I do 1 squared plus 2 squared, I get 5, so radical 5. And to make it a unit vector, if we remember back to our unit on vectors, we simply divide by that magnitude. So my unit vector, that's now moving twice as much in the y direction than the x, is going to be 1 over root 5, comma, 2 over root 5. Well, now that I have my direction, now I need my partials, because really those are the only two parts to directional derivatives. So when I take my partial with respect to x, well, that means that anything with a y is a constant, so I would be able to factor the cosine y out, but then the derivative of x with respect to x is just 1. So I'm going to have 1 cosine y, or just cosine y for my f partial x. And again, pause the video, do this on your own, make sure you're getting the same answer as I am. The partial with respect to y, well, now the x is a constant, so factor that out. The derivative of cosine y with respect to y is going to be negative sine y, so I get negative x sine y for my partial with respect to y. The last step is just to put it all together, to plug in each of my pieces. So I'm going to plug in my partials, and I'm going to plug in my a and my b. And there's my directional derivative. All right. Now, the last step, and we don't want to forget this step either, is that I actually wanted to evaluate, right? I wanted to find the actual slope. If I'm finding slope, that should be just, well, some numerical value. I shouldn't have x's and y's left. So if I want to find the slope at my point 1, 0, then it's just a matter of plugging in 1 for my x's and 0 for my y's. And so when I do that, let's see, I get cosine of 0. Well, cosine of 0 is just 1 minus 1 times sine 0, but wait, sine 0 is 0, so 0 times anything is just gone, so that entire part is gone. So I just have 1 times 1 over root 5, which is just 1 over root 5. And there is my directional derivative. The last thing I want you guys to take a look at, though, is that my directional derivative is the sum of products, which means I can write it as a dot product. I can use my dot product notation here. All right. And if I take my partials, so partial with respect to x, my partial with respect to y, the way I use my dot product notation, I need to take each part and write it as a vector. So these two become the parts of my first vector, and this vector has a very special name. It's called the gradient. And in my next video, we're going to talk about the gradient much more in depth because it's an incredibly important concept when it comes to, well, calculus and physics and engineering and machine learning and artificial intelligence. It shows up all over the place. And so the gradient is a very special one. And then, well, if I take my other parts, the a and the b, well, obviously a and b, that is just my u vector. So that's really all the directional derivative is. Again, we're going to talk way more about the gradient in our next video. If you have any questions, please don't forget to ask.